All right. So, hi everyone. Thanks for joining the IGS seminar today. It's been a while since we've had a sea ice focused one. That is fully on me. We took some time to sort out the schedule this year, and I've been busy with fieldwork and some other things, and so sea ice seminars sort of fell by the wayside, but we're back. So thanks for joining. We've got a couple left for the spring session, and then we'll be taking our usual break during summer, and then starting up again in September or October. So stay tuned to look for announcements on those speakers coming sometime soon. Today, we're excited to have Maddie Smith, a scientist at Woods Hole, who is going to be giving a talk on puddles on a frozen ocean. I'm very curious to see where we go with this metaphor, and yeah, looking forward to it. So, as per usual, please hold your questions till the end. You can either type them in the chat bar or hold on to them and raise your hand, and I'll call on people one by one. As per usual, the seminar is recorded and will be posted onto the IGS YouTube page, usually tomorrow. So if you want to follow up with anything, it will be available to watch again. So with that, I'll pass it over to Maddie.
Thanks for the intro, Dave. Yeah, thanks for joining today. So I'm Maddie Smith. I work as a scientist at the Woods Hole Oceanographic Institution. I mostly work in the Arctic Ocean, studying the physics of the upper ocean and sea ice. Try to do that in an interdisciplinary context. But I really love sea ice, and I think, yeah, it's a really striking and expansive cover on the Arctic Ocean. And despite that, it's only this relatively thin veneer separating the ocean from the atmosphere above, with the average thickness around a meter or two. It has really far-reaching impacts on the Arctic system. There we go. Less visible, but possibly equally important for periods of the melt season are these thin layers of meltwater that can pool under, around, and on top of the sea ice, which can similarly act like a barrier. And the layers under the sea ice and in leads in particular are challenging to see and thus have been often overlooked in observations and analyses of Arctic processes. So the context of these processes, as you're likely well aware, are that the volume of Arctic sea ice remaining in the summer is declining rapidly. This figure is from a recent paper that we have in review, looking at sea ice decline in the Arctic, as many others have, trying in particular to better constrain that with novel satellite observations. So the red show constrained predictions of the timing of an ice-free Arctic, using observations of sea ice freeboard and thickness from ISAT-2, and just showing that the ice-free date might be even earlier when we account for this constraint. But of course, as sea ice still forms each winter, even though the Arctic might become ice-free, annually it can still represent a large flux of freshwater associated with the melt of sea ice that will still form over the winter. I want to contextualize, of course, this melt with the full Arctic-wide freshwater budgets, which have become kind of a hot topic over the last number of years. And so this is showing recent work by scientist Izzy Labrosse to create a Arctic-wide freshwater budget. And it suggests that the sea ice melt, which is separated out in gray here, with a little bump in the summer, is really very minor in comparison to other freshwater fluxes in the Arctic. So for example, river runoff and what color is that here? Anyways, river runoff, precipitation, and glaciers or ice sheets. So even though the sea ice melt is not a positive source for freshwater in the long term Arctic-wide, it can have really significant local impacts. So just wanted to kind of contextualize the scale of freshwater across the Arctic and what we're going to talk about specifically today. But so what does the sea ice melt look like when it's in the ocean on this local scale? We can visualize what that might look like by looking up through a hole in the ice. And at the top of this image, we can see the relatively bright ice that's embedded in this thin layer of the upper ocean. And where just below, we can see this layer of fresher water that's, where the indication of the bounds of this is suggested by this trapped biological layer above the saltier water below. This is a photo that's from July in the Arctic, taken during the Mosaic campaign in 2020. And the layer that we observed here was on the order of tens of centimeters, or just about half a meter. And the accumulation of this layer obviously has impacts for the ecosystem, which you can see in this photo, but also impacts the mass evolution of the ice and transfers of energy, momentum, and gas also across the ocean interface. While these layers have been observed only a number of times over the last 100+ years, it's not widely acknowledged that as this smaller scale is typically smaller than what we would observe, and so it's eluded a lot of the observations that have covered the Arctic. And so the impacts also are largely unknown. So this talk, I'm going to mostly summarize the results from two recent papers looking at these types of freshwater layers across the Arctic and their impacts that have come out over the last few years. And both of these were the result of really large collaborative efforts with the numerous colleagues that are listed here. So yeah, as I mentioned, the observations were all made as part of the 2019 to 2020 Mosaic expedition in the Central Arctic, which focused on understanding the physical evolution and implications of such, physical evolution generally of the system and the coupled Arctic system. And we had the opportunity to focus also within that on the implications of these layers. The results I'm going to show today focus around the summer part of the year long Mosaic drift. So that's the blue part of the map on the left. And the station observations covered all parts of the coupled system. So the little schematic drawing on the right shows what a lot of the types of observations that we would be making from the ice and the surrounding area looked like. The changes in the Arctic climate system were the overarching motivation for this year-long expedition. And we observed the coupled system in this really cross-disciplinary manner over a full annual cycle. And this allowed us to observe all of the full melt process over the summer with this really awesome benefit of knowing everything that had led up to it in the year prior. Yeah. Okay. And just to make sure we're all on the same page, I wanted to start with some definitions of the terms that relate to sea ice meltwater and meltwater budgets. And so in terms of the sea ice melt, we have a number of different sources within the system, starting with the snow that accumulates on top of the ice. And then the ice itself can melt in different ways. So we can have ice also melting from the top, just underneath where the snow would be, but also from the bottom or basal melt or from the sides, lateral melt. So then that meltwater that forms can be conceptualized as kind of spreading across this very heterogeneous sea ice cover into a thin layer, which can include many different sinks, which you can see also in this schematic. So it can accumulate on top of the ice in melt ponds. Similarly, in under ice, what are sometimes called under ice melt ponds or under ice meltwater layers. And then also in the leads around the ice in lead meltwater layers. Sometimes these different layers have been referred to as freshwater layers, but it should be noted that they're mostly not strictly freshwater because they're coming from this ice and snow, which have some salinity in them as well. So here what we're talking about with these thin meltwater layers is relatively shallow, so on the order of maybe tens of centimeters to a meter, and relatively low salinity. So we define this kind of arbitrary cutoff of 20 grams per kilogram, but definitely fresher than the underlying seawater. Also, it's not uncommon for the meltwater to refreeze, potentially at the interface with the colder and saltier water below. So most commonly occurs beneath the ice, but can also happen at the edges of leads, and those are referred to as false bottoms. So and then just to put these type of layers in the context of the stratification you might be more used to seeing at a mixed layer. So the magnitude of stratification quantified by the buoyancy frequency in the upper plot here in blue is significantly larger than what we see in this example at the mixed layer below. So it's really often very strongly stratified and because it's very, very fresh and very discrete. Okay, so then we can put all these different pieces of the system and how it's evolving together to create a more quantitative upper ocean freshwater budget. So just combining all the things that we talked about. So in terms of the sources of freshwater, we have all of the melt coming from the snow, but then also from ice melt on the surface, bottom, and on the sides. The final potential source term is here P represents precipitation. So that's mostly rain during the summer, potentially also snow, but mostly rain in the summer. And then on the right side, we have the different sinks, so where this freshwater can end up. So those can largely include potentially melt ponds on the ice, and then these under ice and lead meltwater layers. We also include here a term for the internal storage in the ice, where the drainage can result in some freshening of the ice itself. And then the kind of residual for all of these terms ends up being the upper ocean term, which is defined here as UO. Having observations of all of these discrete pieces is generally quite a challenge because they span a lot of different spatial and temporal scales. But we were really fortunate from Mosaic to have such high resolution observations of the system to be able to piece together as complete of a sea ice freshwater budget as has ever been made. So our observations were over this flow that's in the map on the right. It was a mix of first year and second year ice that was kind of drifting over the central Arctic over the course of the year. So again, that map is on the left shown as before. So here we're still focusing on that blue part of the drift. So for the source terms, we combined the really broad range of observational estimates of snow and sea ice melt that were made from different methods to make our best estimate of each of these terms. From met station measurements on the ice, we had a few different ways of estimating the precipitation, which were combined into kind of a best estimate as well. One of the novel aspects of the quantification of the melt here was that we made an adjustment for most of the melt measurements are often made on level ice because it's much easier to deploy things. So we did make an adjustment to that, to the underrepresentation likely of contribution from ridges. And then on terms of the sink terms, we had characterization across the flow of both, ridge for that prior term, but then also of the melt pond distribution, both in terms of the area and depth, which we use to quantify the melt pond volume. And then regular profiling of under ice and mead meltwater layers. So those are in the kind of pink lines and then the purple stars on the map. Finally, we observationally constrained with a 1D model estimates of the internal storage of the freshwater in the ice. So this is another novel aspect of what we've done here. First time this has been kind of combined with other observational estimates. So then of course that leaves, we did not make here direct estimates of the upper ocean freshwater sink. It's really, we did attempt, but it is really hard to separate that out because the ice flow is of course drifting, and so over different water masses, which prevents being able to make quantitative estimates of contributions to the mix layer. And so that becomes the residual of the other terms that are directly estimated. Okay, so looking at some of the results from this, in terms of the sources, we have, so sources for freshwater during the Arctic summer include, are shown here on the top as a cumulative freshwater, looking at it sort of in a 1D budget, so an effective thickness of freshwater over the flow. And the black line shows the total of all the terms. And so what you can see is that the largest contribution to the local meltwater was from the surface ice melt, so that's in the teal. Just below that, we have the bottom melt in navy, and then snow melt, lateral melt, and precipitation are all relatively small. The bottom plot shows the same results, just recast now as a fraction of the total. And we generally see the same conclusions, whereby, especially by the end of summer, the majority is from the surface ice melt. One thing this also highlights, though, is the relative importance or fraction of the different precipitation terms. And we note that the precipitation from the summer as rain is a really small contribution, but the stored precipitation as snow still contributes a pretty significant amount. And precipitation is still important to consider, but is much more relevant in terms of that which is accumulated over the entire year. So obviously one caveat of this budget is that we have just one realization from one point in time and one point in space, where we would expect some variability. On terms of the sources of meltwater, there has actually been one other fairly complete estimate using observations from Sheba from 1998 in the Western Arctic. And so here we can compare our observations of the sources from Mosaic with those from Sheba, and the ones in Sheba are now the dashed lines. Surprisingly, they're actually relatively consistent, where we have, by the end of summer, the totals differ by less than 20%. So of course, this is now only 2 samples, so it's not really clear if this is just by chance that these happen to be so similar, or if there's some sort of consistency in the relative contribution of these terms. But yeah, it suggests that in similar ice conditions, we may expect sort of a similar amount of total melt over most summers. Okay, so then where does this locally generated freshwater, which is about a meter total over the summer, end up? So what are the sinks? Observations of each of these have been made, but they haven't before been estimated altogether. And the first thing that you might notice in looking at this plot of all of them together is that the total in the black line is only about a quarter of a meter at max, compared to about the meter total of the sources in the slides prior. So the missing term, the upper ocean, is likely is the residual, and so is likely a majority of the total freshwater, like where a lot of that freshwater is ending up. So very little of the freshwater is probably being retained locally in the melt ponds, which are shown in blue, in the ice, which is the kind of brown line, and then in the thin layers under ice in pink, and in leads in purple. Of course, we still think these layers are important for the system, and melt ponds are an example of that, where we know that melt ponds are really important for a lot of different aspects of the system, including especially their impact on the sea ice albedo. Yeah, and so digging into a little bit in terms of how that term in particular evolves, we look here at the fraction of surface freshwater produced, so the surface and snow melt that could contribute to melt ponds, compared to how much is actually stored there. And what we see is that a relatively small fraction, at maximum just over 30%, is stored in melt ponds, down below 10% by the end of summer. So really most of the fresh water that's available to form melt ponds is being drained to the ocean. But despite this, they seem to have significant impacts for the system. So zooming out a little bit, the prior observations of these layers have been pretty sparse over time and space, but where there have been observations looking for them, it has suggested that they may be common. So the first observations of these began with Nansen back in 1894. And where they observed meltwater layers in leads of about a meter thickness. Meltwater layers in leads have almost always exclusively been observed in July, which you can see in this figure, where the size represents the thickness of the observed layer. And there was also a notable example in the observations from Sheba in that's not 1993. Anyways, 1998, where there's quite a fresh warm layer in leads that was observed. The under ice meltwater layers have been also fairly infrequently observed, and actually most of the observations suggesting their presence are based on observations of false bottoms, which suggest freshwater layers were present underneath the ice. One of the few direct observations was from Einedal in the Canadian Arctic, where they saw observations of around 7 to 13 throughout June. So in the context of these prior observations, the mosaic data set is in part largely unique because it showed the evolution of these layers over time with repeat measurements. And so these layers show the thickness evolution so the lead and under ice meltwater layers were present for the majority of July. This was indicated by a variety of measurement platforms, which are the different symbol types here. The melt ponds in teal represented a pretty small but relatively consistent in terms of thickness meltwater reservoir throughout July. And the profiles on the bottom show how the meltwater layers in the leads in particular evolved over time. We're going from dark purple at the beginning to lighter purple towards the end of July, where the meltwater layer is not only thinning, but also becoming a more gradual halocline, which you can see in the salinity plots on the right. Okay, so we can also look at examples visually of what these under ice meltwater layers look like with some videos. So this first one shows diving through the ice. You can see that there's a bunch of melt ponds on the surface, and we drop the GoPro down through a hole drilled in the ice, where as we pop out the bottom of the ice in a second, you'll see this sort of slushy ice at the bottom, which represents the false bottom just about here. And then below that, you can see this sort of shimmer, which is the meltwater layer, which is indicated by the kind of reflections off the boundary of the halocline. You can also nicely see in this video, I think that these features are occurring over this relatively large level area. So fairly extensive in this part of the ice flow. We similarly saw these features in the leads. And so here you can again, as we saw kind of at the beginning of the talk in that photo, this halocline is here marked by this concentration of biological material. So where it's very green and hazy is where that transition layer is occurring and trapping that, that biological material. And you can see around there's a bunch of ice flows that appear to be kind of melting and contributing to this freshwater layer. There were also freshwater layers observed later in the season during the freeze up. So here you can see that fresher layer, that sort of halocline with platelets growing preferentially and where it's fresher. So the implication of these features for the physical evolution of the system was clear during the observations on Mosaic. So throughout both July and September, the distribution of algae was visibly stratified across the upper 2 meters of the surface ocean, often with community assemblages in the underice or lead meltwater layer that were distinct from the underlying seawater. And so here, these meltwater layers were acting like a barrier with unique stresses for species in the layer. And that also related to changes in the gas exchange processes where the exchange with the atmosphere was concentrated within this layer and reduced with the ocean below. So we can look a little bit more at what some of those implications in the system were. And so starting with the physical side, when the conditions align for such meltwater layers to form in the ocean, we see feedbacks on the physical system. So here this shows the dissipation rate, both where meltwater layers are present, so those are the thinner lines on the left side of the plot, and then where they're not meltwater layers, which are the thicker lines. And the turbulent dissipation rates are dramatically lower when the meltwater layer is present compared to when there is no layer. And it's so the ocean is more well mixed. So the turbulent dissipation is dramatically reduced both within the layer, but also below the layer. So with reduced mixing, we might expect some impacts as well on the exchange on the ice. And so the impact on the ice can actually be twofold, where we see different impacts at the ice edges and underneath. So at ice edges, where we can accumulate heat potentially in these surface layers from solar heating, this can lead to an increased melt of the adjacent ice. We had limited measurements of this during the Mosaic campaign, but this example from Sheba showed really rapid melts by the edge profiles in the lower plot here. And then you can see probably Dawn standing on that undercut ice in the upper photo. Underneath the ice, we see that the meltwater layers can lead to potentially new growth during the summer, which is typically the melt season. So I mentioned earlier these false bottoms that can form underneath the ice, and we saw a number of occurrences of these. And so area where there were false bottoms are shown averaged in the red compared to a nearby area that did not have meltwater layers where there was dramatic melt observed. And so, so this can over the summer temporarily halt or even reverse the typical bottom melt that we would observe. And so these changes then also have impacts on the ecology of the system. And visual observations revealed a concentration of biological material at the interface trapped between the meltwater layer and the seawater below. So we had a really unique opportunity to sample across this interface to understand the impacts on the community structure. So this was work led by Amelia Chamberlain and others kind of on the eco side. And so you can see that in the salinity structure here. And then the results in the figure on the right summarize the relative eukaryotic community abundances across these layers. She also looked at the prokaryotic, which show similar trends. And the key points are that, these show the distribution in the meltwater interface and seawater. And we see in general, a unique community present in the meltwater layer that is more similar to what we see in the sea ice community. And then on the right, we see that the interface layer community structure is qualitatively very similar to the underlying seawater, which is likely a result of the interplay of the physical dynamics of the aggregation of material at that interface. Yeah, that we can see in the photos and videos. So these results then tie in with potential implications for how species might react to these meltwater layers higher up the food chain. And so two examples of this that we saw are the diatom Melsia arctica, which is shown in this series of photos, where we observed that these diatoms both deteriorated and became detached from the ice over time, coincident with the formation of these meltwater layers. Yeah, so these can disintegrate into smaller aggregates. And later we observed that algal aggregates were floating within the meltwater layer, which other papers have shown to be active biological hotspots and food sources. And so these may then support copepods and even polar cod, which have been observed to use the meltwater layers above false bottoms as a refuge, potentially to avoid predators. So you can see, yeah, an example of that in the photo where there's some polar cod in the background here, kind of hanging out in that gap space between the main ice pack and the false bottom below. So finally, what are the implications of this stratification in the physical environment for and in the ecosystem for the biogenic gases? So this plot just shows an example profile from freeze up from September of the DMS as one example of this. And over the upper 1 to 2 meters where we had significant stratification, so that's shown in the salinity in the left, you can see that really clear stratification. The DMS concentrations on the right are significantly lower at the surface in those lower salinity waters. DMS is an aerosol precursor, and so it has a significant climatic impact. So this is, yeah, potentially an important change within this meltwater layer. The other gases that we observed almost all showed changes in concentration with the meltwater layer, but not necessarily all in the same direction. There's like no unifying trend in the direction of the change. But taken together, these suggest that there's a decoupling of the atmosphere and the deeper ocean, which impact the concentration and exchange of these very climatically important biogenic gases. So in future work, we hopefully will be able to focus more on addressing specifically how the meltwater layer might act as either a permeable or impermeable layer with both the atmosphere above and the ocean below. Okay, so to summarize the new work that we summarized in these two papers, we were able to combine a really diverse number of data sets that were collected on this campaign, which allowed us to estimate a relatively very complete sea ice freshwater budget. On the source side, we saw that it was dominated by surface melt, which is in agreement with previous observations from Shima. But on the sinks, we saw that most of that meltwater is still incorporated into the ocean. There's relatively very small fractions that remain in melt ponds and in leads and under the ice, probably around 5%, less than 5% each. But of course, those still significantly impact the system in a number of ways. So on the physical side, that can include changes to summer ice growth by increasing false bottom growth, but also slowing the ice melts. And it can also reduce the vertical momentum fluxes into the ocean. They can also then impact the coupled system, so where it acts as a potentially a physiological barrier for growth, where it impacting the ecosystems. And we also saw a capping effect, reducing the atmosphere-ocean gas exchange and aerosol production. So these impacts make it really important to be able to well represent in, for example, coupled global climate models, where some of these processes could have potentially large feedbacks on the change over time. But yeah, there's still a gap in observational tools and process studies to be able to fully understand both the extent and impact of these features. So I want to talk a little bit just to finish about those different aspects. And so to get a sense of how well models might be representing at least some aspects of these features, we compared outputs from a climate model. So here we used CSM2 with the observations. And so we're using 10 years of the model outputs from a location that was near where mosaic happened. And so observations are in the points. from both Mosaic and Sheba, and then the model range are the kind of shaded bars behind. In terms of the total, the sources of meltwater are actually pretty similar between the two, but you can see that it's flipping the relative contribution that we would expect from surface and bottom melt. So the teal and blue are kind of opposite in terms of their relative contribution. And so this may be important for aspects like representation of melt ponds, which come from the input of surface meltwater rather than bottom melt. And so models don't explicitly represent a lot of the sinks of these freshwater, but they do. Most models do represent melt ponds because they are so important for albedo. And so we are able to compare the representation of melt ponds in the model as a fraction of the meltwater stored compared to what we saw in our observations. And so this shows that temporal evolution of the fraction of meltwater, where we see that the fraction in the model is dramatically underestimating what we saw in the observations. So this is a target of ongoing work that's being led by David Clement Sewell, particularly for the CSM model, but hopefully something that we can improve in other models that are being used as well. And so how do we expect these might change? The meltwater might change in the future of the Arctic. So here we look at that again using the CSM2 model, looking at outputs from three different future scenarios in terms of this total snow and sea ice summer meltwater flux. And so the colors on the map show the trend over that time period from 2015 to 2100. And in general, we can see that the meltwater flux is expected to increase around the margins, or decrease around the margins, and potentially increase in the very middle of the Central Arctic Basin. But of course, the propensity or possibility of forming meltwater layers will depend on other factors that are also likely to change, like wind and ice drift, which can drive mixing. So so notably, most models can't explicitly resolve the features that we're focused on in this work and in this talk because of their very small vertical scale. So more research and development will be needed to be able to resolve and understand the impact of these features on the large scale in the rapidly changing Arctic. And so this will rely largely on new observations, which we already have really awesome opportunities to make more observations to contribute to this. And so one of these is the Contrast campaign, which is led by Marcel, Nicholas, and others at Avi, which will be happening this summer to take observations throughout the summer in three sort of regimes that are typical of our changing Arctic. And so we plan to measure meltwater fluxes and their impacts under these three regimes and how they evolve. And hopefully this will be one piece of helping us better observe and understand these features and how they might change in the future. So that's all I have. Thanks. Happy to take any questions.
Great. Thanks, Maddie. That was excellent. Samuel, yes, you can lead us off.
Sorry, that was a mistake. I was trying to hit the clapping button and I hit the wrong one. But great talk, Maddie. Thank you.
Yeah, thanks, Sam.
Anyone else have any questions? I guess maybe I'll get us started here. Maddie, measuring lateral melt seems like you mentioned that it was sort of one of the limitations of what you could do during Mosaic. And I'm sure we've all seen that figure and that picture of Dawn standing on the melting ice edge there, measuring the lip topography or whatever we're going to call it. Are there any newer methods for measuring this, or any better ways to try to constrain that idea of lateral melt?
It's a good question. We did, so I would say that on Mosaic, I felt like we kind of missed this. We made some sort of rough estimates. I did have. I was trying to get back to that slide. I think it's on here. The Sheba observations are on there too. But we did make sort of an estimate just based on the aerial observations of the size of the flow. I mean, so if you image it from above, you can estimate the area and the kind of average thickness, you can sort of get a ballpark. But it's very challenging to make these high resolution lateral melt estimates, especially in conditions in which it's you might have dynamic, there might be pieces breaking off as well. And so I think that doing like on the larger scale, using the satellite methods to do that better and kind of separate those out might be one way we can get larger scale estimates, and how that varies as a function of ice types. But potentially similar methods on the smaller scale, like using types of imagery that we can, from drone surveys or, um, other, stations that we might make locally could help provide estimates that, I think the best we still have is those kind of edge profiles that Dawn and others have sort of manually made at the ice edge, which work very well, but are definitely time consuming. So hoping to continue to improve on that in the future.
Okay, interesting. Stephen.
Yeah, Maddie, very interesting talk. I seeing how, all these different accounting for all the different sources and sinks of fresh water. And I was surprised to see that snow was a small contributor. But what about just looking at the ponds, the surface ponds themselves? How much of their water comes from snow melt?
Good question. That's sort of part of what we tried. Well, it's kind of the opposite of what we tried to get at here. Because I mean, what we looked at here is how much of the total meltwater, both snow and surface melt, is stored in the ponds. But I suppose to get at what you're asking in terms of how much of that is snow versus sea ice, you would need to probably look at a combination of the salinity and maybe the like delta 18, especially in ponds that are not yet connected. And I'm not sure if we made the observations to be able to do that. I would guess that it largely varies over time. Obviously, at the beginning of the summer, there's large contributions from snow where it's melting very rapidly. But then later, as the snow is largely melted, that would change. So I guess it would probably be a pretty big evolution over time, but I don't know that we've specifically quantified that.
Okay, thanks.
But good question.
Okay, Sam's had a minute here to think this through, so he's back up.
Now he's got a question. Oh, now you're muted.
There we go. I'm having a bad Zoom day, apparently.
Yeah.
I was wondering, okay, so my interpretation, tell me if I'm wrong, but these like very thin meltwater layers are kind of able to persist because they're getting trapped in the leads between flows. And so, if that's right, is there some point where the flows or like the ice is broken up enough, the leads sort of become somewhat discontinuous, and these shallow meltwater layers are no longer able to persist near the surface? Or is that like, what does the evolution of that look like from when you have these layers to when you don't have them?
Yeah, so I guess the big caveat being that the observations that I'm showing here are from one example evolution of how this might happen. But I think the big thing that we saw here is that the, kind of calm winds are one of the, obviously the big things that you need for these to persist. And so there's probably a combination of things over the whole space of the Arctic that can contribute to these breaking down, either a storm that causes mixing, both just kind of from the wind waves in the lead, but also from causing more motion of the ice, which can mix it up. But also, and I think that could also potentially be driven by just the ice concentration becoming low enough that it mixes away more easily. I think, I guess as I sort of touched on with these being observed so sparsely, it's hard to know on the whole how frequently these occur. I think these observations would suggest that they might be more common than we would expect, but we would definitely need more observations to confirm that. There has been some like idealized modeling to try and get at how those processes evolve. And so I think there's definitely an opportunity to work on scaling that up with kind of the typical conditions that occur across the Arctic to understand from that side how frequent they could be. But I don't know that that's been done.
Thank you.
Mm-hmm.
Anyone else? Any other questions?
I have a question. I just don't know how to raise my hand.
Okay. Yeah, go ahead, Ellen.
Ellen here. Thanks. I had a question about, you said that the meltwater storage in ponds is underestimated in models. Do the models like compensate for that somewhere else, or is it overall underestimated?
Yeah, so I think what we hopefully I don't get this the wrong direction. So I think that what we saw is happening in the models is that the representation has them as too thin but too extensive, and so yeah, there's basically some like compensating errors in how melt ponds are currently represented. The volume is yeah, the volume is very low, but the fraction is potentially too high. So that was yeah, mostly shown in the kind of the work that Melinda led from the mosaic observations. So, you know, there's a variety of things that we need to improve the kind of, yeah, evolution, both in terms of the volume, but then also getting the physics of the optics right, which are currently probably too, yeah, anyways, I'm getting confused about directions. But yeah, so there's some things that are compensating for each other that could be improved. But yeah, they're largely too thin, but too extensive.
Yeah, and albedo's too high or something.
Yes, too high. Yes, that's the right direction.
Okay, that makes sense. If they're
Yeah.
if thin, then they would have a high albedo and smaller volume. So that, yeah, okay. Okay, and then I have another question. Like, how would you think this is a big question, and it's okay if you don't have like a good answer for this, but how do you think these observations would differ in the Southern Ocean?
Yeah, we've talked a little bit about this. I think the conditions are generally very different in the Southern Ocean, so there's often a lot more mixing. There's like just more waves, and most of the ice tends to melt throughout the summer. But from talking to people about it, it seems like there have been some observations of maybe less persistent, but still over short time scales, very, you know, similar thin freshwater layers occurring in the Southern Ocean. But yeah, so I think they're probably less persistent and may also, of course, have different impacts, where there's, you know, generally different communities in the upper ocean and things like that. So that was something that we really hope to kind of build on with future work in this area, with, yeah, cruises that kind of persistently work in that area.
Okay, great. Thanks. Great talk.
Thanks a lot.
Anyone else?
Yep, please. Hi, I'm Pat Langhorn. Maddie, that was lovely. How often did you see any freezing at the interface between the fresher water and the saltier water? Was there just too much heat in the water to allow that to happen, or did it happen quite often?
So sorry, you're asking how often did we see these sorts of
Yeah,
false
these
bottom
platelets or platelets forming at the interface between the fresher and saltier water.
I'm just trying to pull up this. Do you mean, so, okay. Yeah, so in the summer, we saw the false bottoms kind of over about 10% of the flow, I think. I wish I don't have these numbers like immediately at the top of my head anymore. But we didn't see a lot of the platelet formation, obviously, in the summer. During the fall freeze up, I think the platelets were pretty, I wasn't there, but I think the platelets were pretty extensive throughout the leads, but was a pretty like quick transition during that freeze up time period. So it wasn't like seen as persistently in time as the false bottoms were in the summer. I don't know if that answers your question. Like,
Yep, no, it does.
okay, yeah, cool.
Excellent. Last call. Anyone else? All right. Well, thank you very much, Maddie. That was a great talk. And I would encourage people to follow up with the two papers that you pointed out there, Smith et al. 2023 and 2025, for more information on this. So thanks everyone for joining this week. We've got 3 more installations of the seminar taking place over the coming months. So check the IGS page for that and follow along on CryoList and wherever else these get posted. Next week we've got 3 talks from a group of 3 early career scientists, so that should be quite nice. And then Yeah, and then if you know of anyone who's interested in giving a talk, please encourage them to reach out to me or Tavy, and we'll do our best to fit them into the fall and winter schedule as we start to plan that. So thanks again, everyone. Take care and have a good day.
Thank you.